So we're going to talk about seismic waves, earthquake waves, what we feel in earthquakes. And to do that, we need to introduce some vocabulary to get some basic concepts related to waves. So a wave, as it says, is a disturbance that propagates in space and time. And waves have velocity, that's how quickly the disturbance moves. They have amplitudes, that's the height or the size of the disturbance. And a wavelength, that is the distance between successive peaks. We'll see on a subsequent slide a pictorial image of a very simple wave, such as described in this equation here, where y is the output, that would be the ground motion, how much the ground moves. X is the distance the wave has traveled, and t is the time that the wave has traveled. And you may remember that the sine function is an oscillatory function that ranges between -1 and +1. So if we multiply that by an amplitude a, we can scale the size of the disturbance. So again, x is distance, and t is time, v is the propagation speed. So now let's look at that in graphical form here on the next slide. So here we have the simple sine function displayed. And we see, again, the amplitude, which is a. Here is the height on one side of the wave. And the wavelength lambda is the distance between either successive peaks, as shown here, or conversely between successive troughs. So the sine function ranges when the argument, that is the quantity here in parentheses, is 0, the sine is 0. And when the argument goes all the way through to 2 pi, then we come back to 0 again. That's one full cycle, one full wavelength of the wave. So as the quantity here, x minus vt, changes, then either we're going farther away on the wave, or time is increasing and we oscillate back and forth. And the proportionality between distance and time is the speed here, v, the speed that the wave propagates. So when you look at this equation, can you think about which direction the wave is propagating? Is it propagating to the right, or is it propagating to the left? Why don't you think about that, and we'll discuss that in class. And also, let's think about what you would do to change the direction of the equation. How would you modify this equation to change the direction that the wave is propagating? Okay, so fundamentally, there are two ways that you can think about a wave. We can look at fixed space at different times, or fixed time and look at how the wave varies with space. So the view number one is a fixed time snapshot. So suppose you're out, and these are water waves, you're sitting out on the ocean on a surfboard, and you snap a picture, you would see at that instant in time, you would see the waves, the crests and the troughs of the waves as you looked out at the waves. The alternate view would be to take a fixed point in space and look at how the wave varies in time. So that would be if you measured your height as you bobbed up and down at a fixed location on your surfboard. As the wave passes underneath you, you'd go up and then down as the waves go through. So again, we can look at how the wave varies in both space and time, and the velocity is, the speed of propagation is what relates the two. Okay, so we have to introduce some vocabulary that is the period and the frequency of the waves. The wave period, t, is defined as the wavelength over the velocity. And that's very simple to remember because we'll realize that the wave has the period has units of seconds, and the wavelength has units of meters or kilometers, and the wave speed has units of meters per second. So if you prefer, you could rearrange this to write that the wavelength equals the velocity times the period, and that should remind you of something you probably learned a long time ago, that is distance equals rate times time. So the units here, wavelength is units of distance, the speed is units of velocity or rate, and time has, or period has units of seconds. So it's fairly easy to remember this simple relationship between the period of the waves, that is the time between successive peaks along the wave, and its wavelength and its propagation speed. The frequency is the inverse of the period. So instead of having units of seconds, it has units of 1/seconds, or cycles per second, which is often expressed as hertz. So 1 hertz is 1 cycle per second. That means 1 wave is passing per second time. So there are different kinds of waves, and all waves need something to generate them, some disturbance to cause the waves to begin propagating. And they also have associated with them a restoring force, something that brings the medium back to equilibrium. So as I'm speaking now, my vocal cords are perturbing the density of the atmosphere, either causing it to be compressed or rarefied. And the resistance of the air to compression is what provides the restoring force. So we call those acoustic waves. Water waves, the kind of waves we were talking about on the surfboard a moment ago, those are gravity waves because gravity provides the restoring force. If we were to bulge up some of water on the ocean surface, gravity would want to pull that back down. And so that provides the restoring force for both wind-driven waves, and as we'll get to later in the course, tsunami waves are also gravity waves. I want to remind you that sound waves do propagate in water, so you can, a single medium like water can have multiple kinds of waves. There are sound waves or acoustic waves that propagate through water, as well as gravity waves on the surface of water. Seismic waves are what we call elastic waves. So the elasticity of the Earth provides the restoring force as seismic waves propagate through the interior of the Earth. And it turns out that because solids resist both compression, as do gases and liquids, which is why acoustic waves propagate through gases and liquids, but solids also resist shear, that is side-to-side motion, and we'll illustrate that with a slinky in class. So because solids resist distortion in both compression and shear, we end up with 2 different kinds of waves called P waves and S waves. So again, seismic waves are elastic waves. The elasticity, the stiffness of the Earth provides a restoring force, and this gives rise to 2 fundamental kinds of waves that propagate through the Earth: P waves, or primary waves, which are compressional waves; shear waves, or secondary waves, we call S waves. Both of those exist in earthquakes. So it may seem counterintuitive that something as hard or as stiff as the Earth is elastic because we don't think about it as being very spongy or compliant. But in fact, materials such as steel or granite, even though they're very, very stiff, they do resist distortion and are elastic. And we'll talk about elasticity more in the course.